The title of this presentation is Asymptotic Thermodynamic Stability of Large-Scale Next-Generation Quantum Systems. To begin with a presentation overview, in this part of the presentation of this series, we'll be describing another connection and drawing upon some differences, some similarities, and obviously differences as well with the previous presentation on the series on synthetic biology and the role of thermodynamics as an interpretation and as a framework for strengthening and for increasing enzymatic activity and preventing enzymes from being sluggish. But in this part of the presentation of the series, we'll also demonstrate how there's another connection between statistical mechanics and quantum physics through thermodynamics that could be more rigorously described beyond this more general framework that we're going to provide and describe, which goes into play of various adaptations and interpretations of thermodynamics, whether it be for more the rigorous types of notions of integrability and other properties that we demonstrated previously in the earlier parts of the series, besides the presentation, the first part of the series in which we were talking about integrable probability. And to do this, we'll be drawing upon material from previous APS March and April presentations, and this will help us highlight other potential connections of interest for research between quantum physics and thermodynamics and statistical mechanics, like we had just alluded to. So we can start out with just some general information and observations about different quantum systems, such as the one which is being used by industry leaders at Google Quantum AI, like how they have in their office at Goleta or other locations, in which they're interested in fabricating different types of qubits that they soldered together on the Sycamore chip. And this chip that's this proprietary chip that's fabricated by Google Quantum AI, it's of interest for being able to potentially usher in a new generation of quantum computation and quantum simulation on next generation devices. The number of physical qubits that are soldered on the chip itself is 52, but due to the fact that obviously when we're encoding and trying to process information on a quantum computer, there's a thermodynamic element that comes into play from statistical mechanics also, which could be of interest to more rigorously justify and quantify, because out of the 52 total qubits that are used on these chips that Google Quantum AI fabricates, there are only 13 or 12 of them that can actually be used for computation, which demonstrate that there's already a very strong hurdle and a very big difficulty in trying to scale up this architecture to millions or hundreds of thousands of physical qubits, let alone hundreds of thousands or millions of logical qubits, which is a more difficult goal. And they arrange these qubits as is shown on the left from a bottom-up perspective in their dilution refrigerator by having several types of wires that connect together for connecting different types of qubits that are built on their Sycamore processors, such as what's shown on the right. And in another presentation on the channel, I drew and mentioned several types of interesting connections between probabilistic programs, because essentially quantum computing can be viewed as a type or of a class of probabilistic programs, because it's related to the fact that we're performing time evolution on some qubits. And from these qubits, if we want to sustain their pristine quantum nature and be able to determine whether there's any potential quantum advantage that we can have from these new types of exotic systems that we don't fully understand due to the limits of quantum mechanics, and how having information with infinite precision of the same time at the position of the momentum of a particle or components of a quantum system is not feasible. Probabilistic programs can also provide us the opportunity to be able to construct different types of objects that we can time evolve and try to extract information from, which can highlight different types of similarities or different types of advantages or disadvantages from classical and quantum methods of computation. And this is a list of probabilistic programs such as Python Monte Carlo or Pyro or NumPyro, or even TensorFlow probability, which takes advantage of the fact that as in TensorFlow, from a more algorithmic perspective, we can instantiate neural networks and we can watch the convergence of the training error of this neural network in TensorFlow when we're feeding this network a certain training set data. So this is exhibiting how really under the hood, there are a lot of types of similarities between methods or methods of computation and simulation means that are used in data science, which can have connections with being able to maintain some precise thermodynamic control, like the thermodynamic control that we mentioned for how thermodynamics appears in the previous biological systems that were defined and described and introduced in the previous presentation, and how also this thermodynamic interpretation can even come into play in quantum physics and being able to help our machine learning classifiers or other types of algorithms perform classifications appropriately and make good precision, or make precise and good recommendations. And we had also discussed throughout other parts of the presentation that the beta equations come into the picture with statistical mechanics in the vertex models, and the 6-vertex model and the 20-vertex model, because these types of systems they exhibit how we can make use of the algebraic beta ansatz, which is an ansatz which positions ourselves in a favorable initial configuration or initial position of the solution space to determine how thermodynamic qualities and properties from the condensation or the root density approach from the roots of the beta equation can be studied, and how this relates to conformal field theory, which also has connections with quantum mechanics and quantum computing. So this is exhibiting how we can maybe begin with a type of property of a material, such as like the property of these qubits that we want to time evolve, in determining whether there's any asymptotic thermodynamic stability, or as we'll exhibit and draw the viewer the attention to from a previous presentation later in the presentation in this series, how we can look at globally asymptotic pure states and how that very much can be related to and characterized in terms of certain properties and characteristics of the thermodynamics of the quantum system, and how that very much relates to types of thermodynamics that we were looking at in initially motivating and vertex models. And like we had mentioned, the CFT, or the conformal field theory sectors, they can come into play with quantum systems, but even they can come into play initially at first through an application to the spin chain, because in the quantum spin chain, we can characterize how setting two parameters which we introduce in the model to be 0 is corresponding to the ground state, which in the phase diagram of the conformal field theory, it's relating to the state with the minimal energy. And this is very much helpful for a quantum system or next generation or large scale quantum system, because when we're looking at qubits, we want to be able to characterize their behavior in a very thermodynamically stable way. And in maintaining this type of thermodynamic control and stability, we're looking at whether, if we perform certain excitations away from this ground state, whether we would still be able to extract information in a meaningful way. And so even from the conformal field theory perspective, with the lower and higher rank spin chains, we can perform excitations by either exciting or changing the magnitude of one of the parameter H1 while keeping the H2 parameter fixed. Or conversely, we could also look at holding the H1 parameter fixed and varying the H2 parameter, or we could even perform the most dramatic type of excitation from the ground state, in which we vary H1 and H2 parameters at the same time simultaneously. And the quantum circuit diagrams are given by the fact that, as is shown in Qiskit, we can even make other types of connections and being able to experiment with quantum systems which are characterized by their quantum volume. And quantum volume is a term developed by people at IEBM and experimentalists, because every type of quantum computing industry leader has different types of metrics and properties of the quantum system that they would want to be able to characterize and study. For one, maybe Google, some would say that Google would have slow or lower error rates than the IBM counterpart in their qubits, because they use a different type of quantification metric, as well as using the aspect of these qubits for performing different types of algorithms that could result in a quantum supremacy speedup, like they said, which is again ultimately relying on there along very favorable thermodynamic properties existing for these qubits in their quantum systems, and whether they would be able to scale this up to larger systems to still maintain this pristine quantum nature that they can extract measurements from and control the thermodynamics of, is still a question that's very much of interest, that even the Qiskit developers are thinking about as well, in that they provide some type of open source architecture which can be allowed to quantify the error rates of different qubits within a quantum circuit architecture, like we had discussed in a previous presentation. And there are several quantum circuits for a variational quantum algorithm that I talked about in the previous presentation, in which in this presentation, which was the first one, I was giving a very detailed overview of the different parts and components of the quantum circuit and how we can try to extract measurements through a distribution of the Pauli Z, of the hat of the Pauli Z gates, which are resulting from the fact that we can extract some information which we can piece together to form a computation on a quantum computer by collapsing the wave function along certain circuits or along certain registers of the quantum circuit. And Lubash et al. Was the reference that I used, in which, as it's given here, the paper is titled Variational Quantum Algorithms for Nonlinear Problems. And it's related to several steps in which they look to formulate a cost function by expanding the norm, which is given first for the nonlinear Schrodinger's and the Invited-Burgers equations, in which they describe how to obtain the cost function, which can then be used to perform some state-of-the-art simulation on a couple of qubits, which they then discuss would be of interest to determine if this type of algorithm could be applied for a broader range of nonlinearities. But besides obtaining the cost function itself, they also have to think about, and we have to think about when we scale up the implementation of their algorithm, is that we have to optimize the ground state, which is relating very much to the types of things that we had talked about in statistical mechanics, in which even from conformal field theory as well, we can have an interpretation of a ground state given when we set some parameters to degenerate, to be to zero, or we either look at ways to minimize the thermodynamic interaction or contributions from one state in within the ensemble of configurations that we would like to sample. So this is very much demonstrating how, even though we're in a little bit of a different setting and different constraints, the fact that we even looked at L operators in the two-dimensional case from several previous parts of the presentation, and the fact that they were expressed in terms of Pauli bases, and in fact, also the Pauli Z basis, which is used as the measurement gate for a quantum circuit, it's demonstrating how there are some very deep and more profound connections between quantum mechanics and statistical mechanics and thermodynamics, and how it'd be of interest to further characterize performance of these quantum devices and next generation quantum devices from a more rigorous perspective, rather than just running some type of algorithm to extend the computations that were given from Lubash et al. But still, having these types of simulations to generate approximations for PDs and systems of PDs from the Lubash et al. Paper, it's at least demonstrating that there's some very reassuring quality and property of this quantum algorithm, but whether it would be able to pan out and extend and play nicely with the thermodynamics of next generation quantum devices is still up for consideration and still up for grabs from experiments and next generation devices that are being developed. And as we had mentioned and alluded to, this is relating to the fact that the main type of problem that or obstacle that we are faced with when we're looking to just extend the algorithm for Lubash et al. From a more naive perspective is that we want to look at measurement extraction for approximating PDE solutions. And it's given, roughly speaking, by the correspondence that we want to be able to correlate some type of quantum readout, like from the circuits that we had described, and how we can distribute the Pauli Z gates to obtain some type of rough repeated measurement on, or rough repeated some measurement extraction from some time evolution on average of a quantum circuit. And we want to be able to compare this to the fidelity of a classically computed PD solution. And this is given like by this reference of physics world, in which we're trying to really control very precisely some properties of subatomic particles and determine how we can make use of information, or how we can potentially realize quadratic or exponential speed up to various information processing tasks, and how, as given from this nature picture on the other part of the slide, we run into the conundrum of the fact that it's like Schrodinger's cat, because when the wave function collapses, we're not really sure exactly in which state the cat is, and it's actually in a superposition of being dead and alive before we open the cat to determine or to observe what its fate is. And this is relating to the facts such as given in this representation of the Bloch sphere, is that the extraction and the measurements that we want to extract from the wave function, it's going to fixate randomly on some orientation within the Bloch sphere when we're performing the readout to obtain some type of measurement before we even know if this measurement has high fidelity or not. And the properties of the gap, or the globally asymptotic pure states, is given by the fact that, as given in this reference that's given on the left-hand side, we need to look about how to be able to stabilize and extract measurements appropriately from highly entangled states. And this is given from the fact that, as in statistical mechanics and thermodynamics, as we've been talking about, and hopefully it won't come now as a surprise, is that we can look at some Hamiltonian and some tensor product representation of the Hamiltonian. And there's also an associated MME, or the master Markov equation, which is given by the fact that we can look at the time derivative of the density. And the time derivative of the density is very helpful because it can help us make sense of entries of the density matrix, which relate to obtaining probabilities or sampling configurations within the Hilbert space, the underlying Hilbert space in which we're doing quantum mechanics. And it's relating to the probability of the wave function, which is also proportional to the probability of observing a particle with some fixed position of momentum confined within some region of space. And in this case, the MME has contributions from both the commutator and the Lindblad operator, which is related to some standard facts about quantum mechanics, in that we want to commute the Hamiltonian, like how we can decompose the Hamiltonian into J components, as given here, with the density, with the time-dependent density rho of t, while also looking at contributions from other operators with the summation being over k. In the open quantum system framework, it's related to another very short preprint that I did earlier last year around, I think, September or August, on eigenvalue attraction. And it's relating to the fact that, again, from this next generation hardware that's being developed by Google Quantum AI, to be able to generate or extract some meaningful measurements and stabilize highly entangled states, that's as given in this reference from 2012, we have to be able to look at ways to localize, to prevent noise from accumulating and prevent thermodynamic instability, and very much exert thermodynamic control over quantum subsystems, and being able to scale up this desirable thermodynamic characteristics and desirable thermodynamic behavior to larger quantum subsystems, which hopefully, as in the case of what Google is trying to do, trying to develop a next generation quantum device, which can operate on hundreds of thousands of physical qubits and also hundreds of thousands of hopefully logical qubits at the same time. And from possible behaviors of standing wave solutions, one possible application of the variational quantum algorithm that we can run on a state-of-the-art quantum simulator is that we can look at generating different wave interference patterns, whether it be smooth periodic or peak periodic, where the distinguishing factor between smooth periodic and peak periodic is that we can see that there are different curvatures of the solution profile for this wave equation, for how which ultimately determines the manner in which how the wave propagates from solutions to the Komatsu-Home partial differential equation, which is a third order highly nonlinear partial differential equation that we were able to obtain a cost function for, which can be optimized, which is ultimately can be related to a thermodynamic type of question if we want to actually be able to run this cost function and time evolve the cost function for generating some meaningful measurements that can be extracted on real quantum hardware, in comparison to a simulator, which can kind of be at sometimes not very realistic, and it doesn't have noise, which is extremely unrealistic because quantum systems and other types of experimental systems are abundant with noise, which must be addressed. And increasing the number of time evolution steps yields quantitatively similar results, in which you can run the time evolution of around 15,000 time steps of evolution from various different time step sizes of the optimizer. And by using the Nevergrad optimizer, which is an open source optimizer from Facebook, we're able to make use of different types of properties of the optimization routine in the classical quantum optimization loop that we had alluded to on a previous slide, which can help us generate some type of noiseless measurement extraction, which serves good as some type of precursor to more realistic results in measurement extraction that can be extracted from a next generation quantum device that we have to exert some thermodynamic control in, which has to have some thermodynamic stability in the asymptotic limit as we take more qubits to be involved and active in the system. In our QFT ansatz, which is meant to denote the initial solution state of the Hilbert space that we use when we apply the variational quantum algorithm, is dependent upon CNOT gates, rotation gates, and Toffoli gates. And it's initialized before the first iteration of the algorithm from before we compile or time evolve this circuit for the first time, so that we can position the quantum simulation in a favorable state for maximizing coverage of the Hilbert space. And I wanted to close out with the future directions of interest that I had given and also discuss in a Dartmouth Applied and Computational Math seminar near the end of 2022, in which related to these types of questions of discussions and connections between machine learning and deep learning and other types of generative and novel or newer trendy types of algorithms. We were thinking about, on the lines of our discussion, whether there are any other quantum algorithms with a more significant speed up in runtime, and that would relate to, on the statistical mechanics side, if there are any types of quantum circuit arrangements that can preserve the favorable thermodynamic qualities of smaller quantum systems that we can extract measurements efficiently from. And relatedly, how many qubits will we require for the optimization procedure? This is to say, this is interesting to think about and to say, because in the variational quantum algorithm paper, in which we extended the algorithm at Lubash et al., we only ran the simulations for like around 20 qubits, and we are already running into some difficulties on the hardware that I was using to run these simulations. But it would really be interesting if we had more computational power, whether there would be any types of difficulties, and what would be the roadblock or the hard wall that we would hit in terms of the number of qubits that would make running the quantum simulator on the variational quantum algorithm obsolete. And finally, would quantum algorithms with faster runtime still deliver high fidelity solutions? So if the question, or if the answer to this last bullet point is no, or if we see that there are very discouraging experimental results in the next couple of years from industry leaders in quantum computing, it would then relate to certain thermodynamic characteristics and qualities, because we wouldn't be able to generate or to fabricate a type of arrangement of qubits on some next generation quantum device that would be thermodynamically stable enough to extract measurements efficiently. And thanks for watching.